Yeah, hi and welcome to my talk about LISA Phasemeter based on MicroTCA as ground support equipment, the development status. I give this talk on behalf of our team working at the University of Hamburg and DESY, and we are funded by the German Aerospace Agency, DLR, and the corresponding ministry, of course. And yeah, let's jump right in. This talk is about the LISA Phasemeter. Here on the right you see the elegant breadboard model of the LISA Phasemeter that we developed in Europe in 2014. I just wanted to run through some of the core functions of the Phasemeter. The most important one is, of course, to provide phase readout for photodiode signals for up to 48 channels. And this phase readout needs to be done with a high precision of 6 microradian per square root of hertz at this frequency range. To do this, we need an ADC jitter correction. We need thermal control, because at these frequencies, getting this kind of phase precision requires very stable analog components, and then we require thermal control to get there. And we also need to read out clock tone sidebands to correct all kinds of clock noise and clock jitter noise in the constellation to, in the end, be able to actually achieve this kind of phase readout precision overall. The Phasemeter also needs to generate and distribute all of the constellation timing signals for the exact same reason, and that is also one of its core functions, and this typically also requires thermal control of several components. It also is used to provide data transfer and pseudo-ranging via pseudo-random noise modulation onto the laser, and it also contains the delay log loops to read out the ranging signals from this pseudo-ranging. It also needs to provide beat note acquisition via a fast Fourier transform, so to actually find the laser frequencies and to set up the constellation. And it also needs to perform filtering and data decimation, and finally also needs to control the laser frequencies. That's just a very short run through of what the Phasemeter needs to do. The LISA Phasemeter developments, currently there's a bigger, most important development, that is of the LISA Enhanced Phase Measurement System, the EPMS, or also towards the flight hardware, and this is done by my colleagues at the Albert Einstein Institute and in Denmark, and this is basically the development up here. And what we're doing in Hamburg together with DESY is we are basically developing this LISA Phasemeter simulator or ground support equipment phase measurement system, GSE PMS, how I will call it through the rest of my talk, and I basically want to talk about that here in this talk. Just to let you know, these developments are not separate from each other. They co-coordinate very strongly. So we try to develop a similar and closely coordinated system in the end. So what is the idea behind this ground support equipment phase measurement system? We want to provide a Phasemeter for technology development and assembly, integration, verification, and testing of the mission. The system should be flexible, multi-channel, so we aim for up to 64 channels. We want to provide it in a kind of semi-commercial way, such that it's available to all LISA partners and they can come to us and basically purchase one. It should have laboratory interfaces and software, so you'll be able to use such a Phasemeter not only with SpaceWire interface, but with a Python interface and Ethernet with the lab computer. And we hope to be able to provide full EPMS functionality and simulate all of its relevant interfaces so that we could actually, quote-unquote, fully replace an EPMS in testing. I brought you here two diagrams. Here on the right, you see the interface control document overview of the EPMS. So here you see all of the electrical interfaces it has to all of the surrounding components, like the optical bench, the laser, the computer, and the power switching unit for the photodiodes. And what you could do, for example, is you could want to test this together with something that talks to the optical benches, like an OGSE or far-field OGSE, and all of this here could be controlled by a GSE PMS, and that could even be synchronized to one of the EPMS Phasemeters used in here. Or alternatively, since we want to fully simulate all of the interfaces you see here, you could also replace the EPMSs in any test with the GSE PMS or even two of those. And these are just some example use cases. There are a number more you could imagine, just to give you a taste of what we want to actually build and achieve with this system. Yeah, the conceptual design of this is based on the so-called MicroTCA .4.1 standard. The standard basically consists out of a crate system that you see up here. And these crate systems provide power and interfaces, and they basically take in modules either from the front or from the rear side. Yeah, this here is the rear side. And the front side is shown here in this diagram on the left in the sketch, and the rear side is here shown on the right. On the rear side, there's an additional backplane used in the MicroTCA.4.1 standard. And this backplane is used to distribute clock tones or calibration tones or any other precision tones or clock signals between different modules. And this is exactly what we also need for the LISA Phasemeter simulator. So we also use this type of backplane. Then we have a number of modules that we use. Most of these are commercially available. And just to highlight a few, we have a central CPU module here where most of the processing, the low speed processing is done. And then we have these FPGA modules here. These are also developed by DESY, but for our project we just purchased them. And these one actually contain the FPGAs that do the high speed processing like the phase readout and so on. And then here on the rear side, we have a number of modules that we're currently developing for this, actually 3 specific types. One type called the ADC module, one DAC module, and one FDS module. And I will tell you more about the development status of these in a moment. And this is basically just an overview for you. If you're interested in the system, this is roughly how it will be assembled in the end. So throughout the system, we need timing and data flow. These are important aspects of the Phasemeter, and all of this we can implement easily with this MicroTCA infrastructure. This is also why we chose to use it, and I won't go through all of the details here. But importantly, you see here, we have this FDS module that actually provides most of the tones of the systems and is driven by USO or by the space-time clock. And this one is then distributing all of its tones through this RF backplane that I just mentioned earlier to all of the critical modules that we built ourselves that provide the flight hardware-like interfaces. And the data flow is mostly happening through the front backplane, so through the standard architecture of MicroTCA, and most of the data is in the end accumulated in the CPU, where it is then read out via Ethernet, for example, with the Python user interface on a computer. So the most important module is the one we've put in most of our time yet. So this is a DRTM-LISA-ADC, and this one will basically provide an 8-channel readout of photodiode signals. So this could be 8 single-element photodiodes or 2 quadrant photodiodes, and this will do so with all functionalities that we will need. So these modules can do AC readout, of course, but also DC readout, and it will also have variable gains to change the gains of the AC signals. The front end that we've designed here has ultra-low crosstalk, so less than 120 decibel of crosstalk between different channels, which we hope we can also achieve in the hardware, but this is just based on the schematics. And actually, this whole thing here has a modular design. It consists of 3 submodules. One is a carrier board that you see here. Then we have a clock distribution module that you see here, has this L shape, and then 2 ADC submodules, so to say, that each read out 4 channels. And we built it like this because we identified some criticalities in all of these, and if one of these doesn't work as we wanted to, we can replace just the submodule and reuse all of the rest of the design. All of this will be cased and shielded and isolated thermally and also isolated from humidity. So this is why here you see this copper housing, and in the end this will be fully isolated here with probably some aluminum casing. On this, we have running an active temperature control that we tested in an evaluation board, and this should achieve less than microkelvin per square root of hertz temperature noise within the critical areas here down to very low frequencies as we need it for LISA. And we currently are finishing the layout, and soon, towards the end of the year, we want to start to produce these modules and then hopefully test them early next year. We also have the DAC module. This will actually later control the laser and PRN modulation signals and send everything out that the laser needs. It will also provide power supply and control for the photoreceivers or the switching units. And this one actually has no critical performance requirements. It's just something that we need to build and test. And we are currently working on the schematics of it. And here you just see an early sketch of how it will look like. The frequency distribution module is another very critical one in terms of performance, since it will generate the pilot tone, clock, and synchronization signals. Many phase noise critical parts of it will be also thermally stabilized and sealed, as I've just shown earlier. So we will use a similar approach there. And we are already doing some component tests for it where we think, okay, these components should be used. They need to be very phase stable. Let's shortly test them. And here you see a concept drawing, which is based on the system that DESY already built for another project, the MicroLog, and we will build something similar that we will then use in the end in our Phasemeter. Yeah, so I already come to the summary and outlook. So the development of this Ground support equipment phase measurement system is well underway. We expect to have the first hardware tests in early 2023 or at the end of the year, depending on how long production will go. We still have to do a lot of software interface and algorithm work, and we do that in close collaboration with the EPMS development. And we're actually soon circulating a document that you see over here on the right, the CDIR document that describes this whole system that we are building and developing in a lot of detail, so that we will provide to all relevant partners so that they can take a look and see, okay, we can use it like this, or we need maybe some modifications. And so if you're interested in this, or if you require a specific function or so, please contact us and just write me an email. And also, I can just recommend to you to listen to another talk from Darsow-Fromm from our team, who's talking about component testing and programming of this Phasemeter prototype. And this is already it. Thank you for listening to my talk.